Welcome to iLecture Online and continuing with our concept of moment of inertia. Again, to remember, moment of inertia is the entity that an object has that makes it difficult for it to rotate. Just like an object that is big in mass is hard to move, an object that has a large moment of inertia is hard to rotate. And the general equation for an object that's a distance r away from the point of rotation, we can say that I is equal to m times r squared, noting that m is definitely a factor in the moment of inertia, but r is more so a factor that the farther away the mass is away from the point of rotation, the more difficult it is to rotate, and therefore the larger the moment of inertia. So then I have drawn on the board here a number of different objects or sets of objects, and how do we find the moment of inertia in each of these cases? Now, here I drew something where we have four objects attached to a small thin bar, and we're going to assume that the bar has very little mass, so that is not important. What would be the moment of inertia of one of these things? And you can say that the moment of inertia here, I, is simply equal to the sum of all the masses times the radius, or we can take the individual moment of inertias and simply add them together. So this would be equal to m1 times r plus m2 times r plus m3 times r plus m4 times r. Notice we simply add the individual moments of inertia, add it all together. That's the total moment of inertia of this structure. Now, what would happen if the r's weren't all the same? No problem. If one r was bigger than the other, we just notate that by using different r's there. Again, the moment of inertia, the sum of them is simply the sum of the individual moment of inertias. So, pretty straightforward. Now, what do we do when we try to find the moment of inertia of something look like this, like a thin bar that has mass m and length L? Now, I'm not going to show you how to actually come up with that equation. I'm simply going to give you the equations and kind of give you a feel of why that makes sense. Notice that not all the mass is distributed at the very end of the point of rotation. It's distributed evenly like that. So some mass is very close, some mass is far away. So in this case, the moment of inertia, I, is equal to 1/3 the mass times the length squared. So moment of inertia is 1/3 ml squared. Now, on to the next one. Here's things a little bit different. Now we're going to rotate that very same bar with the same mass and the same length about a point in the middle of the bar. Now, what does that mean as far as the moment of inertia? What it does is it moves the mass, in essence, closer to the point of rotation. So the closer the mass is located to the point of rotation, the smaller the moment of inertia. So therefore, you would expect the moment of inertia of this one to be less than the moment of inertia of that one. And indeed, it is. I, in this case, is equal to 1/12 ml squared. Notice how close everything is to the point of rotation. Now you say, well, 1/12, isn't that a small number? Yes, it is, because we take the total length and not just the radius from the outside to the point of rotation. So that is the correct value. Now, what if the bar is not a thin bar like that? What if it's kind of a wide bar, like a plank, like a wooden plank that's rotating about the center of the plank like this? Well, then this equation becomes I is equal to 1/12 the mass of the plank times, instead of using L squared, we use A squared plus B squared, because then the mass is distributed away from the point of rotation this way and this way, so that becomes the equation right there. Moving on to the next one, we can now see that we're rotating this about a point at the very end of the plank. And in that case, it turns out that the width of the plank in this direction doesn't matter, only the width in this direction. And so then it becomes just like this one right here. We can say that I is equal to the mass times this distance, which is A squared. And of course, I'm forgetting the constant in front. It would be 1/3 ma squared. All right, now on to some different kinds of objects. What if we had a solid cylinder that was rotating about its axis of rotation? So we have an axis in there, the whole cylinder is rotating around that, and here we can say that I, the moment of inertia, is equal to 1/2 the mass times the radius squared. So notice again, not all the mass is distributed at the very end of the point of rotation is distributed all throughout, so it turns out it's half the mr squared. Over here, where we have a cylinder that has a hollow portion to it, but has a certain thickness to its shell, we can then say that the moment of inertia is equal to 1/2 the mass times r1 squared plus r2 squared. On to the next object. So now we have a ring that is very thin, where the outer radius is very much the same as the inner radius. So it almost becomes like all the mass is again distributed at a distance r away from the point of rotation. So this becomes I is simply equal to m times r squared, where r is simply r1 and r2, where they're virtually the same. Two more objects to go. One is a solid sphere and the other one is a hollow sphere. With a solid sphere, mass is distributed all throughout the sphere. And as it's rotating about the sphere, of course, it's not like a cylinder. Mass are kind of distributed a little bit differently. And so you can say that the moment of inertia here, I, is equal to 2/5 times mr squared. And if it's a hollow sphere, now you say, well, with a hollow sphere, isn't all the mass distributed evenly around the point of rotation? No, it's not, because it's a sphere, it's not a cylinder. In some cases, the mass is very close to the point of rotation. In some cases, it's r away from the point of rotation. So you can say here that I is equal to 2/3 mr squared. Okay, so now let's see if we see a pattern here. You can see that the moment of inertia either is mr squared or some constant, some fraction times mr squared. It's either mr squared or something less than mr squared. The more the mass is distributed towards the center of rotation, the smaller the moment of inertia. So the smaller the fraction. The more the mass is distributed away from the point of rotation, the larger the moment of inertia, the larger the number here becomes equal to 1. And if all of the mass is distributed at distance r away from the center of rotation, then it's 1 times mr squared. So that's kind of the general principle that we follow with the moment of inertia. So again, quickly reviewing. So mr squared, here you simply sum up the mr squareds. Here, if it's rotating about the end of the bar, where the bar is thin, then it's 1/3 ml squared. If it's rotating about the center, then it's 1/12 ml squared. Then here, when we have a plank that's rotating around either like this or like that, it's 1/12 ma squared plus b squared. And if it's rotating about its end, the thickness don't matter, just the length of the plank, so it's again 1/3 ma squared. If it's a cylinder and it's a solid cylinder, it's simply 1/2 mr squared. If it's not a solid cylinder, if there's an opening in here, like a hollow portion of it, then it's 1/2 m times the sum of the two radii squared, inner plus outer radii squared. If it's a thin shelled ring, then it's again kind of like this, it's mr squared. And if it's a sphere, if it's solid, it's 2/5. If it's hollow, it's 2/3 mr squared. So a nice little review of the different moment of inertias for the various objects. Now I'm going to show some examples of how to actually calculate these values. Of course, for that we're going to need a little bit of calculus, a little bit of integration to do that. So if you're interested in knowing how to do that, stay tuned for the next several videos, and I'll pick some examples of how to actually figure out what the moment of inertias are of these various objects.